A counter function is a function that increases over an interval ultimately, in the sense that f of 0 is strictly less than f of 1, so it does attain some height, although its derivative exists and equals 0 almost everywhere. By mean value theorem, you cannot have the same claim and have the differentiability at every single point. So already this theorem is a counterexample to showing why differentiability at every point is important for mean value theorem. At the end of this video, I will also talk about another reason why such counter functions are significant in analysis. But what I'm going to do today is give a very intuitive geometric construction of an example of counter sets. The other constructions I had seen before were quite complicated. They used decimal expansion of numbers, not really decimal, but they were like write every number in the base 3 and then the counter set corresponds to those having only zeros and twos, and then okay, switch twos to ones, keep zeros, and then change the base from 3 to 2. You can look up the exact details on Wikipedia article, but that is already quite not straightforward. The list of reasons being that some real numbers have more than two representations in a base, and also what does it really mean to keep the same digits and then suddenly turn the base 3 to base 2. What does that exactly do in terms of being an increasing function, being surjective, and continuity, and many other properties. So the construction I'm going to show you is one that I learned from a paper by Pekka Koskela and Kevin Wildrick from 2007. And this is not even, this is not a significant thing in that paper. It's just, okay, there do exist counter functions, but then they give a very concrete formula of how to obtain one. Okay, so we have been talking about counter sets a lot, and the benefit of this construction is that you don't have to have the standard counter set, but you can have it with any parameter lambda, where lambda is positive and less than 1/2. So what happens, remember, you start with the segment 0, 1. You remove the middle so that you end up with two equal line segments, both of length lambda. And then you keep the same ratio so that you will have lambda squared remaining from this blue. So the blue here, you remove the middle, so you end up with two new intervals, and you keep going. So our counter set will be the blue set, the set of points that survive all stages and all removals. The red intervals, which are the removed intervals, are going to be the complement of our counter set. It's often easier to think about the complement of a counter set than a counter set itself, for the reason that the complement is a countable union of open sets, while the counter set itself is uncountable. It's not quite easy to visualize, really. For example, if you take one counterpoint, can you talk about the next one? The answer is no. If you could, it would end up being a countable set. And many other tricky things about counter sets are tough to immediately see. But the complement, again, is just the countable union of open sets. And in this example, in this construction, it's even much better, because we can actually index them in a very consistent and useful way. which could have also potential applications for other stuff you do. So I thought this would be an interesting construction to have in mind. So the way indexing works is, okay, so you put U1, that means stage 1. In stage 1, there's only one removed interval, but I want to denote, give it an index. So U11 is the open interval that was removed at stage 1, if we shall call it stage 1. So remember that this will be the same. This has been removed, and no new counterpoints, of course, will be added here. But then in stage 2, you remove 2 new intervals. So out of each blue in the previous case, so this will be the first stage 2 interval. So this will be stage 2 interval, the second one. And guess what? So if you ignore the previously removed ones, stage 3, there are these tiny little bit of reds removed. So this is stage 3 first interval. This one is stage 3 second, stage 3 third, and finally stage 3 fourth. And then you keep going. So you will have UI, and then you will have J's, where J goes from left to right, just counting the intervals removed at stage I. Now, how many of these do we exactly have? The claim I make is that this is 2 to I minus 1. Why is that the case? Well, it's simply just by inspection. If you want to be extra rigorous, you can do a proof by induction. But also, there's this other argument. It's completely immediate that the number of blue subintervals is going by powers of, so let me follow the coloring. So 2 to 0 intervals, here 2 to 1 intervals. These are now the surviving ones, blue ones, 2 to 2, 2 to 3, and so on. So the number of surviving intervals is 2 to I at stage I. Now, how many new intervals will be removed in the next stage? So that means when you move, so if this is 2 to I, in the next stage, the number of reds, the number of removed ones, so where do removed come from? Exactly for each of the blue in the previous stage, you remove the middle. So the number of removed intervals at stage I plus 1 will be equal to the number of solid ones, the remaining one in the previous stage. So at stage I plus 1, we will have 2 to I many removed intervals. So if I had I plus 1 here, this would be just I. So I have shifted the index back to just I, therefore it's equal to that. So just for the record, the number of surviving intervals at stage I is 2 to power I. And this is the number of removed at stage I. Okay, now what is the construction of the counter set? The counter set is assigns, so the function will be first defined on the complement of we define the function f first on the union over all j and then union over all I of these intervals u, I, j. Of course, j goes from 1 to 2 to I minus 1, and this can go from 1 to infinity. So initially, my function is not defined on the points of the Cantor set, but on the complement of the Cantor set, on this union. How it is done? On u, I, and 1, f is the constant 1 over 2 to I. And then we keep adding 2 to the numerators. So on u, I, and 2, f is the constant 3 over 2 to I. And then we keep going. If you follow the formula, you can see that on u, I, and j, f is the constant value 2j minus 1 over 2 to power I. So notice that with j, this is jumping by values of 2, and it starts at 1 when j is equal to 1. So what is happening here? Let's look at the picture again. Notice that any point that is not in the Cantor set is exactly in one of these intervals and never in two of them. There's no nestedness to them. So you construct the function f in stages. So in stage 1, you assign the value of, so let's remove all these potentially confusing overlaps. Okay, so you begin there. You assign the value of, so this is u1 and 1. So you assign the value of 1 over 2 to power I, 1 over 2. And okay, there is only 1, so you end there. So f is equal to the constant value 1/2 on this red part, and at this point f is not defined anywhere else. In the next stage, we define f on the new intervals. So this is u2, 1, and this is u2, 2. What you assign to this is 1 over 2 to the stages 2 to I equals 1 over 4. And then this is 3 over 4. Remember, you jump by 2 in the numerator. And here, the function is still from the previous one. You don't touch them anymore. So this will not be a sequence of functions, but a sequence of larger and larger domains where it is defined. So you keep the previous values of f here, 1/2, 1/4, and then 3/4 here. So the next 2 to power I is 1 over 8. So this construction is so simple, you don't need to memorize any formula. So the next stage starts at half the previous, and you always start with 1 over that power of 2, and then you add 2's to the numerator. So you get 3 to 8, you add 2, you get 5 to 8, and then you add another 2, you get 7 to 8. You can also see that at the last interval, this will be 1 minus what you started with, which is 1 over 8 in this case. And in general, because, well, 1 over 2 to I, and this becomes 2 to I minus 1 over 2 to the power I. Okay, and this is exactly when j is the last one. So what was the last count in the number of ith removals? J was equal to 2 power I minus 1. But our formula is 2j minus 1 over 2 to I, and that exactly matches. So, and then of course this keeps on going. Ultimately, you will have the function defined on the union of reds. If you have seen the picture, you're thinking, and rightfully so, that why am I over explaining this? This is just obvious, and I hope you've gotten to that point. That's why I stop over explaining. The rest of the thing is to, we have several important jobs to do. One is that if, so these are the claims which are also I'm using exercises to do. So number one, if is a non-decreasing. Indeed, unless you are in the same red part, you make a jump, and that is obvious from the construction. Almost obvious, you have to consider cases. And also, if is uniformly continuous. On this union Uij. And for that, you need to consider case by case. For example, you want to say that if you pick one value here and one value here, and these are pretty close to each other, then f of y minus f of x is less than epsilon, no matter where x and y are located. And that can be done by a case-by-case study. So you have to fix some notation. For example, x is in one stage, so x will belong to some u I, which will depend on x, and some j, which will depend on x, and y will belong to a different I and different j. Now you have to consider cases you can do, for example, without loss of generality. Suppose iy is bigger than ix, so that it is in a shorter interval, and so on. But the reason, the philosophy why this function is uniformly continuous, number one, there is this homogeneity. The picture is the same all along the interval, so it doesn't matter whether you're looking at that picture or this picture. The second is that when you fix a delta neighborhood, how many of stage I intervals can lie between them? There is only a limited number of them, because at the stage I, the length of these removals are 1 over 2I. And only a certain number of them can fit into an interval of length delta, because you have to have delta bigger than that. And then how much jumps do function have along these? The jumps, every time you move from one such interval to another of the same length, the most you jump is 2 over 2 to power I, because you add 2 to the numerator. And then the rest is just bookkeeping and making sure that they don't add up. So because there could be, in theory, hundreds of tiny intervals from x to y. But what you are trying to prove is that the total jumps you accumulate on your way still does not go more than epsilon. And I promise the last philosophical reason for that is simply because the sum of these powers, so you will have a number of 2 to power i's. So suppose you have 3 2 to power I zeros, and then you have 7 2 to power I ones, and then so on. These counts, you will prove that bound that I just wrote, and then basically this will be comparable to this geometric sum. But this geometric sum is at most 2 times 1 over 2 to power I naught, and now if this is large, then this becomes less than epsilon. The details can be annoying, but I don't think they are any worse than the other constructions of the Cantor set. Now, what do these properties guarantee us? There's another exercise that if you have a uniformly continuous function defined on any subset, then you uniquely extend it to a continuous function on the closure. So if uniquely, also here being monotone helps. You can prove it that way too, because if you have a non-decreasing function, there is at every point there is the right limit and there is the left limit. The only way for a function to jump would be to have a disjoint. I mean, to be discontinuous would force the function to have a jump discontinuity, but because we prove this uniform continuity, that cannot happen. So if uniquely extends to a continuous function on the closure of these open sets, which includes the counterpoints, so that it's all of this. F is, this new F is also non-decreasing, just because of the way it's defined. You can approximate a counterpoint by a sequence of non-counterpoints. So if you have non-decreasing on those, you get a non-decreasing also if you compare values at counterpoints. So what else did we want from this function? So if it's non-decreasing, uniformly continuous, it had to be, by the way, uniformly continuous, because if you are just continuous on 0, 1, you automatically are uniformly continuous. So the last claim, that f prime of x is 0 almost everywhere, is immediate. This is because, well, almost every point is not in the Cantor set, because Cantor set has measure 0. We keep the same ratio because in the Cantor set, for example, you can see it from Lebesgue density theorem. Is not in the Cantor set, but then such a point has some neighborhood, so you can do plus minus delta, has this neighborhood that is completely inside one single uij. Well, if x is not in the Cantor set, it's in the union of uij's, so it belongs to one of them. And because these uij's are made up of open segments, that means this point lies in one of these red segments. No matter how small it still has a neighborhood of x completely in there. And then f is constant there. And the root of a constant function is definitely 0. So therefore, f prime of x exists and equals 0. So if you're not in the Cantor set, your derivative is 0. And that was the last claim. Now the promised significance of such a function. You may have already guessed this. We said that the function does go from value 0 to value 1, but it never has any positive derivatives. So that is kind of the counterintuitive thing about it. If our constructions was 1/2 here, and then 1/4, and then 3/4, whatever it is, of course it's very difficult to draw a counter function. This is just the finite approximation how it is built. But remember, ultimately there are no jumps, so it's a continuous function. But then that increase never amounts to any derivative. So some people have also called this devil's staircase, but I don't like those types of terminology. This is actually a beautiful function because it shows us the boundaries and limits of calculus. So what happens with this function is that f of 1 minus f of 0, which is equal to 1, it's insignificant, just that it's not 0, it's positive. But then it is not equal to the integral from 0 to 1 of f prime t dt, because this is just 0. It's 0 almost everywhere. And the integral, whether it's Riemann or Lebesgue, it's 0. And therefore we see that the fundamental theorem of calculus does not apply to this f. And if you had not seen this example ever before, this should shock you a little bit, so that everything you've been taught in calculus could be totally wrong. Of course, mathematicians would immediately jump on the question of what functions, for what functions the fundamental theorem of calculus actually holds, and what is exactly wrong with this function. And of course, they have pinpointed and identified the properties that make a function satisfy the fundamental theorem of calculus in terms of an if and only if theorem. So function will have fundamental theorem of calculus on every subinterval, if and only if, blah, blah, blah. I have covered a little bit of that in the playlist on curves in metric and Euclidean spaces. There we talked about when integrating the speed of curve recovers the variation or length of the curve. The short answer that your function should be absolutely continuous. And this is together one word. Absolutely continuous is the right class of functions where this occurs. Hope you have enjoyed this construction as much as I have enjoyed it. This is very concrete, very easy to remember, and notice that this lambda can also be anything, so you don't have to work with just the standard 1/3 Cantor set. Until next video, have a great one, and please consider subscribing. More on the way coming.